Alkenes, Chapter 8. Alkenes occur when two sp2 hybridized carbon bond. They make a sigma and a pi bond between the two of them, or a double bond. One of the bonds is made by the overlap of sp2 hybrid orbitals, and the pi bond is made by the overlap of the unhybridized p orbitals. Objectives: 1. Sources and uses. 2. Nomenclature. 3. Alkene addition reactions. 4. Synthetic strategies. Your goals. By the end of the chapter, you should be able to indicate sources and uses of alkenes, name and draw alkenes, predict alkene addition products, predict reagents needed from starting substrate to target, write mechanisms, propose viable synthetic routes. 1. Sources and uses. There are numerous sources of naturally occurring alkenes. Acyclic alkenes may occur as alpha-ferrocene, found in a natural waxy coating on apple skins. Cyclic and polycyclic alkenes. Limonene is responsible for the strong smell of oranges. Alpha-pinene is isolated from pine resin and is a primary component of turpentine or paint thinner. C-double bond C are found in structures of pheromones, such as ectocarpene, which is a pheromone released by the eggs of seaweed to attract some sperm cells. Alkenes in industry. We saw alkenes may be synthesized via elimination reactions. Alkenes can also be obtained from petroleum. Alkenes are critical precursors in the chemical industry. Each year, over 70 billion pounds of propylene, or propene, and 200 billion pounds of ethylene, or ethene, are made just from cracking petroleum. And then those are derived into other useful compounds. For example, ethylene is made into different types of alcohols, vinyl chlorides, PVC. Propylene is also synthesized into things like acetone, propylene glycol. 2. Nomenclature. Alkenes are given IUPAC names using the same procedure to name alkanes with minor modifications. The first thing we do is identify the parent chain, which includes a C-double bond C. We're going to end the name in -ene to indicate we have a double bond. Identify and name the substituents. Assign a locant and prefix if necessary to each substituent. Give the C-double bond C the lowest number possible. List numbering substituents before the parent chain name in alphabetical order. Ignore prefixes except for iso when ordering alphabetically. The C-double bond C locant is placed either just before the parent chain name or just before the -ene suffix. Let's go ahead and name the following compound. With this compound here, we have a C-double bond C, and in terms of numbering, we're going to number the parent chain so that the carbons of the double bond get the lowest number possible. They take priority. So we're going to number from left to right, 1, 2, 3, 4, 5, 6, 7. Because there's 7 carbons, we're going to use the prefix hept and the ending -ene. We're going to say heptene. The 2, which is the smallest of the two numbers between 2 and 3, is the locant. So we're going to say 2-heptene or hept2-ene, which tells us the double bond is between carbons 2 and 3. If we say 3, then it looks like the double bond is between carbons 3 and 4. So we're going to use 2. We also have branches. On carbon 5 we have methyls, and on carbon 6 we have methyls. So we're going to also include those in the name. 5,5,6 trimethyl 2-heptene, or we can use that infix, which means we're putting the 2 in between hept and -ene. 5,5,6 trimethyl hept2-ene. Either answer is acceptable. Alkene addition reactions 3. Addition is the opposite of elimination. A reagent adds across a double bond. The C-double bond C pi bond is converted into 2 new sigma bonds. After addition, we end up with sp3 hybridized carbons. Our reactant had sp2 hybridized carbons. Table 8.1 shows you common types of addition reactions, or the types of reagents that can add across a double bond. The pi bond itself is an electron pair donor. We saw that electron pair donor can behave as a base, where the electrons pull off H+, resulting in a negative, or the conjugate base being released, or it can act as a nucleophile, where the pi electrons obtain or attack an electrophile. Addition versus elimination. Addition and elimination are equilibrating reactions. The side that is favored depends on temperature. The higher the temperature, the more important the entropy term becomes when we consider Gibbs free energy. A higher temperature means a bigger entropy term. Elimination then is going to be favored by entropy. Lower temperatures will favor the enthalpy term. Sigma bonds are stronger or more stable than pi bonds, and addition reactions will create more sigma bonds. Note that we lose a pi bond and create more sigma bonds here whenever we have addition. Addition reactions are therefore favored by enthalpy. Note if we were to calculate the delta H of the reaction given here as an example, we're going to see that the delta H is negative 19 kilocalories per mole, in other words, favoring the products. Addition reactions, though, are not favored by entropy. Two molecules combine to form one product and entropy decreases. Reaction favored is temperature dependent. At lower temperatures, enthalpy dominates, and the addition reactions are favored. So if we have low temperature, we're going to see the addition reactions. At higher temperature, entropy dominates, and the elimination reactions are favored. Therefore, lower temperatures are typically used when doing addition reactions. Hydrohalogenation. Hydrohalogenation is the addition of HX to an alkene. HX will be either HCl, HBr, or HI. When HCl, HBr, or HI adds across a double bond at low temperatures, the addition reaction will result in a halogenated alkane. If the alkene is not symmetrical, then two regioisomers are possible, depending on which carbon gets the H and which carbon gets the X. Note up here with the first example, since we have carbon 1, 2, 3, 4, 5, 6, or 1, 2, 3, 4, 5, 6, it doesn't matter which of the two carbons of the alkene gets the Br, because we will get as a product 1, 2, 3, 3-bromohexane, whether we put it here or we put it here, in terms of the Br and the H. But if it's not symmetric or it's asymmetrical, then we have different positions that are possible, resulting in a different product. We have either this carbon here, that's sp2 hybridized, or this carbon here that's sp2 hybridized. Since this one here has one H and this one has no H's, it's not going to be symmetric. So where does the X go? Regioselectivity, Markovnikov addition. Hydrohalogenation is regioselective for Markovnikov addition. In 1869, Markovnikov observed that the H atoms tend to add to the carbon already bearing more H atoms. So if we have this carbon that has more H's, the sp2 carbon, compared to this sp2 carbon that has no H's, then the H of HBr will add to the carbon that has more H's already. So we'll see it adds to this carbon, therefore the other carbon that has less H's gets the Br. The halogen is generally installed at the more substituted carbon. The Br goes to the carbon that has more carbons. HX addition, Markovnikov mechanism. The mechanism is a two-step process. The alkene first must be protonated, forming a carbocation intermediate and a bromide ion. That is done so by the pi electrons extracting the H+ that will result in that carbocation. This is the rate-determining step. The proton transfer requires the most energy of activation. Then there's going to be a nucleophilic attack. The bromide ion functions as a nucleophile and attacks the carbocation intermediate, resulting in the alkyl halide. The step with the highest energy of activation is the rate determining step, which again is the formation of the carbocation intermediate, in this case the first step. Let's do an example problem. Show the mechanism and the product for the following reaction. We have an alkene and the addition of HBr. Go ahead and try and then come back and check. Well, first thing that's going to happen are the pi electrons taking or abstracting that H+, while the sigma electrons become a lone pair of electrons on the bromide ion. This will form a carbocation. The carbocation is going to be the tertiary carbocation and not the secondary, because tertiary carbocations are more stable. That means the H added to this carbon here, that used to be the sp2 hybridized carbon here. Now it's sp3. At this point, the bromide ion acts like a nucleophile and attacks the carbocation center, making a sigma bond between the carbon and the Br. This is going to be our product. Stereochemistry, Markovnikov addition. Hydrohalogenation may result in the formation of a chiral center. For example, consider the addition of HCl across 1-butene. We'll see that on carbon number 2, we have a chiral center now that forms in 2-chlorobutane. There are going to be two Markovnikov products that form in this reaction. The two enantiomers are formed in equal amounts. We're going to get both the R and the S enantiomers. Why? The carbocation intermediate can be attacked from either side of the empty p orbital with equal probability. So that carbocation intermediate may get attacked by the nucleophile from one side or from the other side of the plane, resulting in the two stereoisomers. Carbocation rearrangement. Recall that carbocations can rearrange either through hydride or methyl shifting if they become more stable. For example, when this alkene undergoes hydrohalogenation, the secondary carbocation could rearrange to a more stable tertiary carbocation. And when carbocation rearrangements can occur, they do occur. Note here, the rearranged product is the major product at 60%. The carbocation would have formed here. We would have had a hydride shift resulting in a tertiary carbocation, and that would be attacked by the nucleophile Cl- to form the Cl-C bond. We will still see a little bit of the other product without the rearrangement, but the rearranged product is the majority. Anti-Markovnikov hydrohalogenation. When peroxides ROOR are used with HBr, the opposite regioselectivity is observed, or anti-Markovnikov addition is observed. The reaction mechanism must be different when peroxides are present then. Example, let's go ahead and predict the following products for the given reaction. If we're working with HBr in the presence of peroxides, that means we're going to get anti-Markovnikov. If it was Markovnikov addition, the H would add to the carbon with more H's so that the carbocation may be stabilized. But if it's anti-Markovnikov, that means it's the opposite. We're going to get Br here and H here on the tertiary carbon once the reaction has taken place. So this is going to be our product. Hopefully we all predicted that. The important lesson here is that regioselectivity of HBr addition can be controlled. We may have Markovnikov addition if we use HBr and an alkene that is asymmetric. The Br will add to the carbon that has more substituents. The H will add to the carbon with less. If it is anti-Markovnikov, the Br will add to the carbon with less substituents, and the H will add to that tertiary carbon in this case. Acid catalyzed hydration, or the addition of water HOH across a double bond. When we add HOH across a pi bond in the presence of an acid catalyst, the catalyst that we use is usually sulfuric acid to minimize any problems with the conjugate base. When we have the addition of H and OH, that means we end up getting an alcohol-acid product. This reaction is Markovnikov regioselective. The OH will add to the more substituted carbon of the alkene. The more substituted the carbon is, the faster the reaction. Let's consider the following data. The simplest alkene, ethene, we're going to see that the relative rate is the slowest compared to the other ones that are more substituted. 10 to the 11th is a lot faster than just 1. It is consistent with the mechanism, then, that proceeds to a carbocation intermediate. The mechanism for hydration, then, must begin the same way as hydrohalogenation, where we have abstraction of H+ by the pi electrons to form the carbocation. Then water will act as a nucleophile and attack that carbocation intermediate. But with hydration, we then produce the oxonium ion, which then has to be deprotonated to afford the alcohol product. At this point here, abstraction of H+ by water will give us the alcohol. Stereochemistry of hydration. The stereochemistry of hydration is analogous to hydrohalogenation and for the same reasons. If a new chiral center is formed, we will get a mixture of R and S. As always, if a chiral center is formed in a reaction, that racemic mixture is obtained. Let's predict our products. If we have the formation of a chiral center, and we will when OH adds here to this carbon following Markovnikov addition, we're going to get both the R and S at this carbon here of the alcohol. And we're going to get it in a 50-50 mixture. Addition versus elimination, control thermodynamics. The reactants and products of hydration are in equilibrium. We exploit Le Chatelet's principle to control that equilibrium. If we are synthesizing an alcohol from an alkene, we would use excess water. For example, here, we would have to go in this direction to get the alcohol, dilute sulfuric acid, it's a catalyst, and here, more water. This would push equilibrium towards the alcohol. However, if we want to synthesize the alkene from the alcohol, we would use concentrated acid and not add water to the reaction. If we use concentrated acid and less water, then we come back over here to the alkene. Oxymercuration and demercuration. Markovnikov hydration, the addition of water in the presence of an acid catalyst, has limited application. Rearrangements often occur, giving a mixture of products. Oxymercuration-demercuration is an alternative. Oxymercuration will eventually allow us to demercurate and then have an alcohol product. It has Markovnikov addition of H and OH across a double bond, but there are no rearrangements that occur. The mercuric cation is the Lewis acid in this reaction instead of H+. The mercuric acetate species results in a leaving group leaving, and the mercuric cation species here. Note the acetate is this component right here, that O, C double bond O, and then a CH3, but we're really concerned with what's happening with the mercuric cation. Mechanism of oxymercuration. When the pi bond attacks the mercuric cation, a stabilized cation is formed, and so it will not rearrange like carbocations do. When a pi bond is protonated, carbocations rearrange if they can because we have a carbocation intermediate. But when a pi bond attacks a mercuric cation, we end up having a mercurinium ion, which means we have a little bit of stability carbocation by interaction with the mercury cationic center. In other words, this process here of sharing electrons throughout these three atoms will not allow for rearrangement to occur. The mercurinium ion is an electrophile and can easily be attacked by a nucleophile. Sodium borohydride is generally used to replace the mercuric group with an H group via a free radical mechanism. So the nucleophile comes, attacks a carbon center, releases the mercuric ion, and we end up having the mercuriated species with the nucleophile attack to the more substituted carbon. Two methods for Markovnikov hydration. Acid catalyzed hydration may lead to a mixture of products. H+ in water, we will end up having rearranged and non-rearranged products. Oxymercuration followed by demercuration is a two-reaction sequence that provides the same product as acid catalyzed hydration, but without any rearrangement. So in this case, when we add the mercury acetate in water, and then follow that up by sodium borohydride, we get the product, the alcohol, without any rearrangement. This would have been a primary carbon, this is a secondary carbon, We get the alcohol on the secondary carbon following Markovnikov addition, but no rearrangement. Anti-Markovnikov hydration. Hydroboration oxidation adds H and OH with anti-Markovnikov regional selectivity. Note that this is also a two-reaction sequence. We have the addition of BH3 and THF, and then H2O2 and sodium hydroxide. With this set of reagents, we end up adding the OH to the less substituted carbon of the double bond, or end up with a primary alcohol that's anti-Markovnikov addition product. Hydroboration oxidation is also stereoselective. The H and the OH are added in a syn fashion. The anti-addition is not observed. When we add these reagents to this alkene here, we would get the H and the OH added to the across double bond to the same side. So we would have enantiomers, either the HOH is coming towards us or away from us. But we are not going to observe the anti-addition, so these stereoisomers here below are not observed. Chirality of hydroboration. Hydroboration is stereospecific. Only syn addition occurs. If only one chiral center is formed, a pair of enantiomers is formed by addition to either face of the alkene. So here we would have an alkene that would eventually have a chiral center at this carbon here, and we would get both enantiomers. If two chiral centers are formed, a pair of enantiomers is also obtained. So note here, we have two chiral centers that have formed, and we're going to get a pair of enantiomers as our product. Consider the products of the following reaction. Two chiral centers are formed. Why do we not obtain a mixture of enantiomers? In this case, a mixture of diastereomers is formed because we actually have a different chiral center here. This is the third chiral center. Let's consider boron. The geometry and hybridization of BH3 is analogous to the carbocation. It is sp2 hybridized with empty p orbitals. The difference is that the boron does not have a formal charge. It is 0. The boron atom does not have an octet. BH3 forms a dimer to help fulfill the boron atom's octets. A dimer just means we end up seeing two BH3s interacting with each other a little bit more closely than IMFs. The resonance hybrid reveals a 3-centered 2-electron set of bonds. 2 electrons are being spread out over 3 atoms. B2H6 can be stabilized by using an ether solvent so that an appreciable amount of BH3 is present. The active reagent then is BH3, loosely held THF. We're going to also see that the THF is interacting via the empty p orbital of the boron to form BH3, loosely held THF. At this point, the boron will have a formal charge of negative, and the oxygen will have a formal charge of positive. Mechanism for hydroboration. It follows anti-Markovnikov regioselectivity. The less substituted carbon attacks the boron's empty p orbital, and the more substituted carbon develops a partial positive, which triggers a hydride shift that is coming from the boron. Recall that the more substituted carbon will be better at stabilizing a partial positive charge. Here, we have an alkene. The alkene's pi electrons will attack the boron's p orbital that's empty. At the same time as this attack is taking place, we're going to also see a hydride shift. An H with the sigma electrons are going to attack the partially positive carbon here. This transition state, where we have the boron making a bond to the less substituted carbon, and the hydrogen making a bond with the hydride to the more substituted carbon, resulting in the anti-Markovnikov addition of the H and the BH2. One BH3 reacts with 3 equivalents of alkene because note there's other H's here that can be removed via hydride shifts. The first step is the repeated step for each BH bond. We end up with a trialkyl borane. Sterics also influences the regioselectivity. If we have a transition state that's anti-Markovnikov, note that we have less interference or less crowding if the transition state had been Markovnikov addition. We would have sterics here. Complete hydroboration oxidation mechanism. Here we have the addition of the 3 R groups to the boron center or the trialkylborane. The oxidation state is going to be formed whenever we have hydrogen peroxide and a hydroxide. Those two will undergo a reaction that will result in a deprotonated form of hydroperoxide and water. This O here with a negative formal charge will attack the boron center of our trialkylborane because we have that empty p orbital. This will result in electrons being transferred over via rearrangement, and an alkyl group migrates, causing the expulsion of the hydroxide ion. We'll have a few extra steps in terms of happening to every R group. Finally, we're going to have the hydroxide attack that boron center, releasing OR groups as leaving groups. The OR groups leave one at a time as leaving groups. There's a proton transfer with water, forming the alcohol and hydroxide. Please do not stress about knowing this mechanism. Understand that this mechanism is what eventually leads to the anti-Markovnikov addition of OH across a double bond, NH. Hydrogenation. Hydrogenation means the addition of H2 across a double bond. If we have, for example, this alkene here, and we have H2 in the presence of a transition metal catalyst like platinum, it will go from alkene to alkane. It will become saturated. It requires a metal catalyst. The alkene is reduced to the corresponding alkane. Without the metal catalyst, the addition of hydrogen is too slow due to a very high energy of activation. Note the differences in energies of activation. The one in red here at the bottom with the smallest energy of activation is with the catalyst, whereas the one without the catalyst has a very high energy of activation. Stereospecific hydrogenation. Stereospecific means only syn addition is observed for this. Asymmetric alkene means we're going to have 2 chiral centers that can potentially form. For example, here we have an asymmetric alkene. Addition of H2 over a platinum catalyst will result in 2 chiral centers. Only the stereoisomers resulting from the syn addition are obtained based on how H2 adds. So we're either going to get the R groups coming both towards us or both going away from us because of how H2 added. A symmetric alkene means we'll get a meso compound instead of enantiomers. Here, when we have a symmetric alkene and we add hydrogen over a catalyst bed, we have either both groups, in this case methyl groups, coming towards us or away from us, but they're the same thing. It's a meso compound. The metal catalyst surface binds the hydrogen and the alkene, which explains why both H atoms are added to the same face of the alkene, or syn addition. So here is a diagram that shows that catalyst surface, they get abstracted on the same side of the alkene. More about catalysts. Heterogeneous catalyst does not dissolve in a reaction medium like platinum or palladium metal. Homogeneous catalyst does dissolve in the reaction medium, accomplished by the use of ligands with the metal. For example, Wilkinson's catalyst. Wilkinson's catalyst has a rhodium complex species, and with Wilkinson's catalyst, we will also get syn addition and an enantiomer if we do have asymmetric alkenes to start off with. Recall that the creation of 1 or 2 chiral centers will result in a mixture of enantiomers unless it's a meso compound that's produced. If we have 1 chiral center, we're going to get enantiomers. If we have 2 chiral centers, we're going to get enantiomers, as long as they're asymmetric or not symmetrical. Chiral catalysts. If a chiral catalyst is used, it is possible to synthesize only 1 enantiomer as a major product. This can be accomplished by replacing the phosphine ligands on the Wilkinson catalyst with chiral phosphine ligands. Earlier we talked about the Wilkinson catalyst as being a rhodium complex. Let's take a look at the ligands. The ligands are triphenylphosphine ligands, and there's 3 of them. So here we have the phosphorus, and the phosphorus has 3 phenyl groups or benzene rings attached to each one. So right now it is a chiral. But if we change the ligands into a chiral set of ligands, now we're going to go ahead and have a chiral catalyst. So right now it's symmetric, as we see here in the original Wilkinson catalyst, symmetric phosphine ligands. But here we can add a chiral phosphine ligand. Doing so can help us produce only one enantiomer in the reaction. William S. Knowles won the Nobel Prize in Chemistry with Noyori in 2001. They developed a synthesis for L-DOPA using an asymmetric hydrogenation as a key step. In order to develop L-DOPA, they had to use a chiral catalyst as they added across a double bond in H2. They obtained the S. Roichi Noyori, also sharing that Nobel Prize, showed that the chiral ligand VINAP can also afford one enantiomer with high selectivity. So notice here we're using a slightly different transition metal, ruthenium, but in this case we do have very chiral ligands here, and we can add across the double bond the H2 with 95% enantiomeric excess, or very highly selective for this enantiomer here. Halogenation, the addition of 2 halogens across a double bond. We're adding Cl2 across ethene, resulting in a dihalide. Halogenation is only practical with chlorine and bromine. Halogenation with iodine is poor, and with fluorine it is too violent. Stereoselectivity. Halogenation occurs with anti-addition. Earlier we saw a couple of syn additions. This one will be anti. That means when we add a halogen across a double bond, we're going to end up with one of the halogen coming towards us and one going away from us. And if we have chiral centers, we're going to get their enantiomers. This is also a key step in the production of polyvinyl chloride, or PVC. If we have petroleum, we noted earlier that via cracking we can get ethene. An addition of chlorine will allow us to form eventually polyvinyl chloride, but the vinyl chloride species undergoes polymerization in order to get there. Mechanism for halogenation. Bromine is nonpolar but polarizable. Approach of a nucleophile will induce a dipole. Think of Br2 as a bromine atom bonded to a good leaving group. The alkene acts like a nucleophile. So the alkene acts like a nucleophile, attacking one of the Brs, while the sigma bond between the 2 Brs breaks and forms a lone pair. Only anti-addition is observed, so the mechanism is not consistent with a true carbocation intermediate. If we had a true carbocation intermediate, then Br can attack from either side, but we do not see the syn addition product. Syn addition doesn't occur. The formation of a brominium ion intermediate is consistent with anti-addition. In other words, one of the Brs that did add across a double bond to start isn't only adding to one of the carbons, but a little bit to both. So we have the nucleophilic attack and the loss of a leaving group. Whenever we have this process here, the alkene functions as a nucleophile and attacks molecular bromine, expelling bromide as a leaving group and forming a bridged intermediate called a bromonium ion. The intermediate is kind of like the mercurium ion, and we can see attack then on one of the carbons from the opposite side, or the anti-addition. Br- attacks the bromonium ion in an SN2 process, giving us that anti-addition. So we see here the attack on this carbon, for example, and this group leaving. To finish up that mechanism, we'll see then we have the anti-addition, or on opposite sides, addition of our halogens, plus an enantiomer if we have chiral centers. Stereochemistry, halogenation. Halogenation is stereospecific, and the stereochemistry of starting material determines the stereochemistry of the products. For a symmetric alkene, we can use something like ATM, where A is for anti, trans is our type of alkene, and M will give us the reference to meso. We're going to end up with a meso product. So here, if we have the addition of Br2 on a transalkene, we're going to get that meso product. But if it's cis, we're going to get enantiomers. Halohydrin, the addition of a halogen and OH. Halohydrins will form when halogenation is conducted in water. Water acts as a nucleophile that attacks that bromonium ion instead of bromide. Here we have the same first steps where we have the formation of the bromonium ion and the Br- was released, but now the nucleophile is water. Water attacks one of the carbons, resulting in the oxonium ion. Proton transfer releases one of the H pluses, and at the end we get a halohydrin, or a halide-containing compound that's an alcohol as well, and enantiomers if we have chiral centers. There are so many more water molecules compared to bromide ions when we have this reaction taking place, let's say in water, so the attack of the bromonium ion by water is more likely than Br-. After water attacks, it is deprotonated to yield the neutral bromohydrin product. Here the product is called a chlorohydrin because we've added Cl in the presence of water. Across that double bond, so we have Cl and OH that adds. Regioselectivity of a halohydrin. It is regioselective. The halide adds to the less substituted carbon, and the OH adds to the more substituted carbon. That means the more substituted carbon must be holding on better to that partial positive charge, and water attacks that center. Regioselectivity results from water attacking the more substituted carbon faster than it attacks the less substituted one. So we'll see water is attacking this carbon center here, then it is deprotonated to give us the halohydrin. Why? The more substituted carbon has more cationic character. It can hold onto that partial positive charge a lot better because it's stabilized by the R groups. Anti-dihydroxylation, the addition of two OH groups across a pi bond. Ethylene can undergo the process to form ethylene glycol or a diol through this process. Anti-dihydroxylation of an alkene is a two-step procedure. The first step results in an epoxide. The second step results in the anti-addition of the OH groups or a trans diol, like we see here. Step 1. Conversion of an alkene to an epoxide. We must consider the acid that we're going to be using in a little bit. We have a transition state of the electrons either breaking bonds or making bonds. At the end, we end up with an epoxide. The acid that is used in order to have this take place is called a peroxy acid, and it has the general formula RCO3H. Two common peroxy acids are peroxyacetic acid and metachloroperoxybenzoic acid, or MCPBA. Note in both of these acids we have these three O's. Step 2. The epoxide is reacted with water and acid catalyst to form the anti-diol. At this point here, note that the epoxide has a three-membered ring system. We have the protonation of the O of the epoxide in the acid catalyst, so the electrons pull off H+, the sigma becomes a lone pair, then water can do an anti-attack, or the nucleophile does an anti-attack in an SN2 process, resulting in the anti-addition of the second OH group eventually when it is deprotonated with the water in the solution. If we have two chiral centers, we'll also get its enantiomer. The similarities for anti-addition. Note the similarities between these three key intermediates: a protonated epoxide, a bromonium ion, and a mercurium ion. Ring strain, because these are three-membered rings, and a +1 formal charge makes these structures good electrophiles. All three yield anti-products because a nucleophile must attack from the side opposite of the leaving group, SN2-like process. So the attack must take place from the anti-location, which will result in the anti-addition products. For the syn addition of two OH groups, or syn dihydroxylation, we have to consider that the mechanism must be a concerted fashion one. The reagent that is used for the syn addition is OSO4, but it is expensive and toxic. NMO, or an alkyl peroxide, is oftentimes used as a co-oxidant, which means we can go ahead and lower the amount of OSO4 needed to catalytic amount. Because it's done in a concerted fashion, we end up with the syn addition. This can also be achieved with the use of potassium permanganate, but only under mild conditions or cold temperatures. The synthetic utility of KMNO4 is limited because it reacts with many other functional groups as well. So here is an example using KMNO4 with the active species being the permanganate species. Again, it's a concerted mechanism. This is not isolated, it's a transition state, but in the presence of a base, we end up with the syn species. Oxidative cleavage, ozonolysis. C-double bonds can also react towards oxidative cleavage. Ozonolysis is one such process. Note here we have a double bond. The double bond breaks and we end up with the formation of two compounds where we had the double bond. Instead of having a carbon there, we have an O, and on the other species, we have an O as well. In other words, C-double bond O's form. This is a two-step process where we need to use ozone and then DMS. Ozone exists as a resonance hybrid of two contributors. So this is a two contributors to the resonance hybrid. Common reducing agents include DMS, dimethyl sulfide, and zinc in water. Here is the mechanism of the addition of ozone. Once ozone adds, and then we see the breaking of the sigma bond between the two carbons, resulting in two carbonyl groups. We have the ozonide species that is also formed. A mild reducing agent frees them up. For example, if we have the reagents that we're using here, ozone and dimethyl sulfide, we should see a break here and forming a C double bond O. So here's our C double bond O and C double bond O, and here's our C double bond O. We're also going to see the breakage occur here as well. We should have a break here to form one C double bond O and then the second C double bond O. Anytime we see a double bond, we're going to break that into two C double bond O's, and the bonds are no longer connected between the carbons of the double bond. 4. Synthetic strategies. Analyze the reagents used to determine what groups will be added across a double bond. Determine the regioselectivity. Is it Markovnikov or anti-Markovnikov? 3. Determine the stereospecificity. Is it syn or anti-addition? The more familiar you are with the mechanisms in the Chapter 8 reagents, the easier it will be for you to predict products. Practice one-step synthesis. To plan a synthesis, assess the reactants and products to see what changes need to be made. For the following transformation, give the reagents and conditions needed. Well, we know we need to do an addition reaction because the pi bond is going away and we're making new sigma bonds. We're adding H and OH, and the OH is adding to the more substituted carbon, so it's Markovnikov regioselective. Therefore, the reagents that are needed are water in the presence of an acid catalyst, H2O, H2SO4. Let's do another one. Let's practice with a two-step synthesis. The following transformation, changing the position of the halogen, cannot be done with a single reaction. It can't be accomplished in a two-step reaction sequence. For example, we can take the haloalkane, have it undergo elimination to form an alkene. The alkene can then undergo addition to form the more substituted haloalkane. To do the elimination reaction, the base needs to be carefully chosen. If we choose a base that's strong and sterically unhindered, we're going to get the more stable product, the Zaitsev product. If we use a strong bulky base, like terbutoxide, we're going to get the Hoffman product. Since we want the double bond to be between the second and that third carbon, we're going to go ahead and use the sodium methoxide reagent. So since we know that's the alkene we need, we're going to use a non-bulky strong base. Next, we have to decide the reagents needed to add H and Br. Since we know we need to add Markovnikov, probably HBr will be fine. The overall elimination addition sequence is as follows. We have to use a strong base to eliminate H and Br and form an alkene that's stable, Zaitsev. Then we're going to add HBr so that the Br adds to the more substituted carbon, or the Markovnikov addition. Let's do another one. What if we want to change the alcohol position? Consider the following transformation. The alcohol in the reactant is on this tertiary carbon, but we want it to go onto this primary carbon here and form this product. This is not a simple substitution, addition, or elimination, so processes must be combined. If we have an elimination reaction take place, then we end up with an alkene. We can then have the alkene undergo addition of HOH, but no, we wanted to add anti-Markovnikov, and we want the less stable alkene. Overall, we need to make sure that we first make the OH into a good leaving group. So tosyl chloride and pyridine will do so. Once it's a good leaving group, we're going to use a bulky base in order to get the Hofmann product. Once we have the Hofmann product, we're going to add the reagents that give us anti-Markovnikov addition, the BH3 and THF, followed by hydrogen peroxide and sodium hydroxide for the anti-Markovnikov addition. Let's do another one where we want to change the pi bond position. If we want to change the pi bond from being between carbons 2 and 3 to being between carbons 1 and 2, we need to do several things. The first thing we want to do is addition. Once we have addition and we have an alkyl halide, then we're able to have it undergo elimination, but we have to select carefully our base so that we get the Hofmann product. Anti-Markovnikov addition of HBr is needed in order to get the Br closer to our target carbons of the double bond in our product. That means we're going to use HBr and ROOR, which gave us the anti-Markovnikov addition. Elimination to give the Hofmann product, we're going to use a bulky base like tert butoxide. Key alkene reactions. Make sure that you know the 10 reactions we have covered. 1. Hydrohalogenation Markovnikov. 2. Hydrohalogenation anti-Markovnikov. 3. Acid catalyzed hydration and oxymercuration demercuration. 4. Hydroboration oxidation. 5. Hydrogenation. 6. Bromination. 7. Halohydrin formation. 8. Anti-dihydroxylation. 9. Syn dihydroxylation. And 10. Ozonolysis. Visualize, know, and fill in practice. The 10 reactions we just saw earlier are here, but now with examples. View each reaction and indicate the reactants needed. Then fill in the next slide. Note here we have reaction 1, an alkene forming an alkyl halide in the presence of HX. This one's the Markovnikov addition. In this case, this one's the anti-Markovnikov addition because we have ROOR. We have the addition of water in the presence of water and an acid catalyst, or oxymercuration demercuration. So you want to continue all the way around through all 10 of them. Once you have a good handle as to how you would go from the alkene to the desired product that's numbered, then go ahead and go to the next slide and fill it out again. So go ahead and fill it from memory. Make sure that you keep on practicing until these come with ease. If you have this functional group, how do you get it to become saturated, for example? Or how do you get the alkene to become a halohydrin? So make sure that you know how to go from this species to any of these species here.